Good afternoon, everyone. My name is Asad Osmani, and I am a PhD student at Goethe University Frankfurt, working under supervision of Professor Lina Wiese. I'm pleased to hear presenting the topic as a part of my PhD entitled DNA-based storage of RDF graph data, a futuristic approach to data analytics. Moving forward in this presentation, we will see the effectiveness of partial data retrieval over whole data retrieval from DNA. As we know, both synthesis and sequencing processes are expensive, so compressing data before archival is helpful in reducing both sequencing and synthesis costs. However, if we talk about a movie, an object, or a book that could be retrieved as a whole and compressed before storage, but that is not the case with complex graph data, where we want to execute several queries over them. So keeping future query demands in view, we proposed a DNA-based storage model for RDF graph data, which enables us to retrieve partial information, the information which we're really interested in, rather than whole, by sequencing a subset of DNA strands. Consequently, it reduces sequencing cost and time. So an RDF graph data, basically an RDF graph is a data model which is used to represent information on semantic web. Basically, it is a set of triples, each containing three components: a subject, predicate, and object. So here you can see the first RDF graph data, and we then use ID-based triple storage model, which has two components. The first one is dictionary, and the second one is triple table. So using these, dictionary contains all RDF graph unique string labels in the graph, and the IDs represent the corresponding IDs in the dictionary. So for to speed up the retrieval mechanism, we have replicated the triple table thrice, and here we can see the mapping of our RDF graph data. We have used 28-byte payload data along with the two hidden primers. And with each DNA strand, we have a unique primer address linked to it. And the hidden primers we use actually helpful in moving forward and backward to implement binary search technique. So if we want to find any string using this technique, so we need log base to number of strands. So here is an example of the query, Sparkle query. We want to know about all the subjects who plays for Spanish team. And first we actually translate plays for and Spanish team into equivalent IDs. And based on those IDs, we find the corresponding subject ID, our list of IDs. And based on those list of IDs, we actually convert back to subjects. So against plays for and who plays for Spanish team, we found 3 players listed below. So we can retrieve using this process all the subject IDs. And similarly, we can find property or object strings as well. So here we plot the results using line chart while executing queries over different RDF graph data. And on the right side, you can see the number of mapping strands, and on the next graph, you can see the number of average IO per query, which is less than 1%. So you can see clearly we can retrieve only less than 1% data while retrieving partial data retrieval. Here are some statistical results. Once we perform initial query and then we want to perform subsequent queries. So subsequent queries actually use number of DNA strands which we extracted before, and there are duplicate strands, and the average query actually for subsequent queries reduces as well. This ID-based method actually, this technique suffers from scalability because we affixed or linked one-on-one DNA strand with the primers, so we need as many primers as we have DNA strands. So for large-scale graphs, we need large number of primers, which is quite hard to offer. So for this reason, we actually come up with another method, which is called block-based storage method. The model is similar, which we have seen before, but we associate number of DNA strands with only one primer. So depending upon the block size, what we have number of primers in our hand, we can scale our block size accordingly, and we associate a list of strands with one primer, which is called a block, and depending upon the number of blocks and the height of the tree, we can say, okay, the maximum sequencing runs will depend upon the height of the tree. So here you can see a simple example where we need only 5 primers associated with different blocks, and each block has associated with the dedicated primer address. And using this block-based method, we retrieved less than 1% data for 3 different graphs, and for one graph we go beyond 1%, which is still beyond 2.5%. So we retrieve only 2.5% partial data while running only 2 sequencing runs. So this is the idea behind, and most importantly, partial data retrieval answers the great question asked to Dr. Karen Strauss, which is a researcher at University of Washington, USA, and Microsoft. That is, how will future digital archaeologists sort through things to make discoveries and inferences and things from DNA. So partial data retrieval, in fact, gives us the answer of this question, these great questions. So these are the results which have both techniques produced. So I do not want to go into deeper. So in conclusion, I proposed ID-based mechanism and block-based mechanism to extract partial information from DNA, because DNA is a big container, so putting data into DNA doesn't mean we will get information efficiently. So thank you so much. If you have any question.
Thank you, that was a very nice presentation. Any comment, question, note? Stéphane.
Thank you for your presentation. I'm wondering whether this is only simulations, or did you try to implement this on real DNA?
Yeah, you just, it's a simulation. I use Python code to simulate the results, yeah. So I'm not a biologist to implement into actual laboratory, so it's just simulation.
So you don't plan to do it in collaboration with someone?
Yeah, I wanna do collaboration. So if someone interested, I can make my offer.
Okay, thank you.
Sir, this was your PhD work, I believe, right?
Yeah, it's part of my PhD work. So I am near to finish my PhD. So my PhD topic is actually about graph data encodings using DNA. So I have mostly worked on that. Yeah.
And are you going to stay in the same DNA data storage area?
No. I want to make collaboration, and if we both agree, the collaborator and me agree to work on some topic, I can offer my services to. Yeah, I'm open to work on. Yep. Thank you.
Thank you again for this presentation. Okay.